Since middle school, we've been told a lie. Not a malicious lie, but a simplified one. We've been taught that atoms are tiny solar systems, neat, orderly, and predictable. We imagine electrons as little planets orbiting a sun-like nucleus. But if you could actually shrink down to the size of a femtometer, you wouldn't find a solar system. You would find a chaotic, ghostly world that defies every rule of logic you know. Today, we're going to peel back the curtain. We're going to look at what an atom actually looks like, driven not by circles and paths, but by waves, math, and the strange laws of quantum mechanics. The first thing we have to discard is the idea of the electron as a thing. In our everyday world, a baseball is a baseball. It has a location, it has a surface. But in the quantum world, an electron behaves more like a standing wave. Imagine a guitar string. When you pluck it, the vibration isn't in just one spot. The vibration is the string. In an atom, the electron is a three-dimensional vibration. It doesn't occupy a spot, it exists as a cloud of energy. When we use scanning tunneling microscopes to see atoms, this is what we get. There are no hard edges, no distinct orbits, just fuzzy, glowing mounds of probability. This is the electron cloud. It's the where of the atom, the region where the electron's wave is most intense. And remember, 99.9% of the volume of this cloud is completely empty space. If the nucleus were the size of a fly in the center of a stadium, the electron cloud would be the stadium's outer wall. Schrödinger equation H psi equals E psi. This is the most important equation in quantum physics. It gives us the wave function, symbolized by the Greek letter psi. Psi is the source code of the electron. It tells us the phase of the wave, whether it's peaking or dipping. But here's the catch. Psi contains imaginary numbers. You can't touch it, and you can't see it. It's a mathematical ghost. To turn this ghost into reality, we square it. Divide psi divides 2. This gives us probability density. This is the cloud we talk about. It doesn't tell us where the electron is, it tells us where the electron likes to be. The thicker the mist in our animation, the higher the chance of finding the electron there if we were to suddenly measure it. You might ask, why can't we just look closer and see exactly where the electron is right now? Werner Heisenberg gave us the answer in 1927 with the uncertainty principle. He proved that the universe has a speed limit on knowledge. If you want to know exactly where an electron is, delta x, you lose all information about where it's going, delta p. Because the electron is a wave, it doesn't have a single position until you interact with it. The moment you hit it with light to see it, you kick it, changing its speed forever. This is why atoms must look like clouds. Their very nature is to be smeared out across space. They aren't blurry because our microscopes are bad. They are blurry because the universe is literally made of blurriness at that scale. This brings us to the most famous behavior, the quantum leap. Electrons don't travel from point A to point B. When they gain energy, they don't fly to a higher orbit. They vanish from one probability cloud and instantly manifest in another. It is the ultimate magic trick. And while they inhabit these clouds, they possess a property we call spin. But don't be fooled, they aren't actually spinning like tops. They are point particles with no surface. Spin is just our word for their internal magnetism. In every orbital, you can have two electrons, but only if they have opposite spins, one up and one down. This is the Pauli exclusion principle, and it's the reason why matter doesn't just collapse in on itself. So, what does an atom look like? It is a shimmering, vibrating, standing wave of probability. It is a cloud of maybe held together by electrical attraction. When you look at your hand, or the stars, you aren't looking at solid blocks of matter. You are looking at trillions of quantum waves, whispering in the dark, leaping across shells, and obeying the silent math of Schrödinger. The Bohr model was a great map, but the reality is much more poetic. We are made of ripples in the field of the universe.